All right, so for this video, we are on page 147, and we're going to look at some polynomials and kind of try to figure out what end behaviors to expect from different polynomials. So what I'm going to do is I'll do the first example with you, and then I'll have you try the rest, and then we'll come back together and see if we can kind of summarize the findings. So if I need my calculator, I'm going to go to my y equals, and I'm going to type in, actually, let's do our window first. So I'll hit window. All of these problems are going to use this window here. So I'm going to make sure I have negative 10 to 10 with a scale of 1, negative 10 to 10 with a scale of 1. So my window looks good when I hit window. So then I go to my y equals. I'm going to type in this first function. So I go x to the third, and then I have to arrow over so I get out of that exponent, plus 2. And then I can hit graph. So these first two questions, actually, we don't need our graph for. So the degree of the polynomial is the highest exponent. So in this case, the biggest exponent is 3, so my degree is 3. Then the leading coefficient is the number in front of that highest exponent. So in this case, I would have, right, x cubed was my highest exponent, so then there's an imaginary 1 in front of here, so my leading coefficient is 1. So all of that can be picked up off of our equation. So then the next part is to sketch our graph. So we're just sketching this picture that we see here. So it looks something like this. And it doesn't have to be perfect, just the general shape. So next, when I do end behavior, we're going off of what's happening at the ends of our graph. So remember, x going to infinity means I'm heading this way. So as I go this way on my x-axis, where is the y value going? So as I go this way, my graph is heading up, which means I'm heading up towards infinity. And then as I head towards the negative x values, as I go this way, my function is going down towards negative infinity. So that would be my end behavior. So what I want you to do is try to fill in as much of this as you can using your calculator and what we just went over. So pause the video, go through as much as you can, and then we'll come back and talk about our findings. If you do not have a calculator in front of you, you are always welcome to use Desmos.com, DEMOS.com. That will also graph functions for you. There's also an app on your phone that you can download. It's called Calculate 84, and it looks identical to the calculators that we use. So either of those options in case you don't have your calculator with you. Okay, so in case you don't have a graphing calculator or you can't make these graphs yourself, I've provided the graphs for you. I just typed all the functions into the calculator and got these values. Some things to consider: if you type in your function like I did here, and then I hit graph, so I typed in that last function here, and I hit graph, and I get a syntax error symbol. If I hit enter and I go back to y equals, we want to make sure that that first negative here is using that negative at the bottom. To us, a negative and a subtraction sign means the same thing, but to your calculator, it does not. So we have to always start with the negative, and then throughout the rest of the problem, we can use that subtraction symbol. So that would be why you would get a syntax error if that happened to you at any point. But hopefully, you were able to get these graphs. If not, here they are so that you can complete the rest of this page. So again, if you're not to this point, pause the video now and fill in the rest of the information and then come back. All right, so these are the values that we should have then filled in for the rest of this page. If you'll notice, all of your degrees are odd numbers, right? They're 3, 5, but this works for any odd number. So it could be 3, 5, 7, 9, 11. Any of those would have the same rules that we're having here. So if you notice, if you look at your top 3, right? And we'll kind of fill in the summary based off this information. So odd degree, which all of these are, positive leading coefficient. So if you look at these top 3 are our positive leading coefficients. They all have the same end behavior. No matter what the degree is, no matter what the fact that the leading coefficient is positive, but it doesn't matter the number that is positive, just that it's a positive number. Our leading coefficient is the same. And what it is that anytime we have an odd degree leading coefficient, it's always going to go negative on this side, and then it doesn't really matter what it looks like throughout the middle, but it's going to go positive on this side. So the end behavior is always going to be positive infinity when x goes to infinity, negative infinity when x goes towards negative infinity. So then if we think about, same thing, odd degree, but negative leading coefficients, that's these negative values here. Now my end behaviors are still also all the same, but they're the opposite of what we just did here. So now we're starting at positive infinity, and then it doesn't really matter what the middle looks like for end behavior, but then it ends over here. So we can kind of summarize that in odd degree polynomials, both ends go in opposite directions. So when we have a positive leading coefficient, it's at negative infinity, it starts at negative infinity and works its way up. When it's a negative leading coefficient on the left, it starts positive and works its way down. All right, so we're going to do the same thing if we flip our paper over. So now we're going to have to fix our window a little bit. Our window here is a little bit different. So if I go to window, I need to be between negative 10 and 10, and then negative 15 and 15. So this is the window I need to complete the back. So we're going to do the same thing we did here. So I'm going to type in this first function. So I have x to the fourth, and I arrow over to get out of the exponent, minus 9 x squared minus 4x plus 12. So the degree, remember, is the highest exponent, so in this case would be 4. Then my leading coefficient, since there's not a number, it's an imaginary 1, positive 1 here, so my leading coefficient is 1. So again, I'm going to sketch my graph, and it looks like this when I sketch my graph. So then from this sketch, I can go ahead and state my end behavior. So as x goes towards positive infinity, so as I go this way on my graph is heading up towards infinity. And then as x goes towards negative infinity, right, my x value goes towards negative infinity, my graph is also working its way up towards positive infinity. So again, like we did before, pause the video, go ahead and try to fill in as much of this information as possible, and then we'll come back and kind of summarize our findings. So again, in case you don't have a graphing calculator, you could have used Desmos.com or that Calculate 84 app, but these are what your graphs should have looked like. So if you want to go ahead and copy those graphs down, you should then be able to complete the rest of this worksheet. So pause the video and come back when you're done. All right, so this is what we should have gotten when we finished the rest of this investigation. So looking again like we did on the front side, if I have an even degree positive leading coefficient, so all of these have an even number degree. So this works for any even number, even 8, 12, 10, all of those. Positive leading coefficient means we're going to look at these first 3 problems, right? All of these have a positive leading coefficient, and we can see that all their end behaviors are the same. When I have an even degree positive leading coefficient, it doesn't matter what's happening in the middle here, it's always going to go to infinity on both sides. It's going up and up on both sides. So then if we look at our even degree but negative leading coefficient, we see they also have the same end behaviors, which means that they're going down towards negative infinity on both sides. Again, the middle does not matter. And at this point, we're not determining what the middle piece looks like, but we can know by the leading the degree and the leading coefficient what the ends of our graphs are going to look like, and then later we can figure out what the middle sketch is. So when we have an even degree polynomial, both ends go in the same direction. So what we've determined is by the degree and then by the leading coefficient, we can determine what the ends of our graph are going to look like. And then throughout the rest of the unit, we'll figure out how to find our x-intercepts, y-intercepts, and continue to make this sketch of our graph. But we know just by looking at the degree and the leading coefficient, we can immediately determine end behavior. So hopefully this helps and you can move on to your next practice.